So the next framing question, or important question, where we left off last time, we left off last time talking about the differences between meiosis and mitosis. The big difference in the goal of them. Now, some of you on the quiz question, which I got all the quizzes graded up to this point, some of you on the quiz question ignored the actual question. Because the actual question was, how does meiosis 2 differ from mitosis? And many of you wrote, how does meiosis differ from mitosis? And that wasn't the question. And so you probably lost some points, and it's because you didn't address the question and focus in on a particular point. Because last time we talked about meiosis 1 is the part where you actually cut the DNA in half. And the way you accomplish that is you don't line all the chromosomes up single file. You line the two versions of chromosome 1 up side by side, and the two versions of chromosome 2 up side by side, and chromosome 3, so on and so forth, all the way down to your X and Y chromosome line up side by side, or your two X chromosomes if you're female. And what happens during meiosis 1 is you don't separate sister chromatids, you separate the two homologous chromosomes from each other. So that by the end of meiosis 1, you have one cell that has the paternal chromosome, and your other cell has the maternal chromosome. Now, yes, on top of that, the maternal and the paternal have mixed a little bit, so you actually have a combination. But after meiosis 1, you've already cut the DNA in half. Meiosis 2 is identical to mitosis, with the exception of you only have 23 chromosomes instead of 46, because you cut the DNA in half during meiosis 1. Okay? Other than that, meiosis 2 and mitosis are identical. So now what we need to talk about is which chromosomes will actually form pairs, and what happens if they don't separate, if you don't actually separate those pairs during meiosis. Okay? So here's normal division. And the answer to the first question is like chromosomes participate with like. Yeah, so the chromosome 1, two copies of chromosome 1 associate together, two copies of chromosome 2. And so here's normal division. During meiosis 1, you take your full complex, and we've got, you see during meiosis 1 we are separating our homologous chromosomes, and during meiosis 2 we now separate the sister chromatids, and so we get at the end of both meiosis 1 and meiosis 2 4 haploid genetically distinct cells. Okay? And we're like, cool. But if they don't separate, like check this out, during anaphase 1 or during meiosis 1, both copies of this chromosome got pulled to the same side. Do you see that? Which means during meiosis 2, when you split these sister chromatids, when they all line up single file, one of our cells that will then produce 2 only completely missed that chromosome. Look, it's only got the shorter chromosome. It doesn't have that longer chromosome. You see that? 2 of our cells are completely missing that longer chromosome. 2 of our cells have an extra copy of that chromosome. Okay? They got it instead of the other one. This is called nondisjunction. Okay? Now, nondisjunction, if it happens during anaphase 1, all 4 of our cells are messed up. All 4 of our cells have an abnormal chromosomal number. Do you see that? 2 of them are completely missing that longer chromosome. 2 of them have an extra copy of that longer chromosome. And you're like, that's no big deal, right? Because a normal cell has 2 copies of the chromosome and now has 2 copies. But what happens if this develops into a sperm, and this sperm goes and fertilizes an ovum that has 1 copy of this? Now you have 3 copies of that chromosome. That's not normal, right? It's normal to have 2 copies. Does that make sense? Or if this develops into a sperm and goes and fertilizes an ovum, instead of having 2 copies of that big chromosome, you'd only have 1. And that's not normal. It's normal to have 2 copies of it. Okay? So if nondisjunction happens during meiosis 1, all 4 of your cells are messed up. If nondisjunction happens during meiosis 2, unless it happened to both of these cells, but in this case it only happened to this cell, only the cells that descend from this one are messed up. Okay? This one's missing one, this one has an extra copy. These 2 are normal because the nondisjunction happened in this cell during meiosis 2. This cell went through meiosis 2 normally. Okay, the sister chromatids separated properly. These gametes are normal. These gametes have an abnormal chromosomal number. Micah and then Levi. Nondisjunction is almost always the result of a failure of the kinetochore microtubules to attach properly. Now, we have our M checkpoint, right? One of our checkpoints ensures that they're attached properly, but there's a way in which you can trick it into thinking it's attached properly, and it's really not. And let me show you that. I want to show you. Okay, let me show you. So here's a cell. And what are these? Well, they're centrosomes, and then the microtubules are going to grow out of here. Okay, right? Yeah. Okay, so let's say here's our chromosomal pair. Okay, so here's, and we're just simplifying this. We've only got one set of homologous chromosomes in that cell. Now check this out. So you might have this kinetochore microtubule attached to this one, and if it was done normally, you'd have another one from here attached to this one of the homologous pair. But what happens if this happens? That one goes over and attaches there, so there's no way the checkpoints checking to ensure that microtubules are attached to both chromosomes, but they are. It just so happened that both of those microtubules came from the same equator. Okay, it came from the same pole. There's only one equator. Gosh. Both of those microtubules came from the same pole. Okay? So it tricked the checkpoint into saying everything's good, but when anaphase happens, both of those are getting pulled over to that side. Because both chromosomes are attached to the same pole. Does that make sense? So you've tricked the checkpoint into thinking it's cool, right? Kinetochore microtubules are attached to both, like they need to be. It just so happened that both microtubules are coming from the same pole. Okay? And so, it's not good. It's not good when this happens. Most of the time, most animals cannot tolerate an abnormal chromosomal number in very many of the chromosomes. There's only one that has a decent survival rate in humans. There are two more that have a very unusual survival rate, but you do get some people with those chromosomal illnesses, except for the sex chromosomes. And we'll see that in just a minute. Okay. So just to sum this up. Homologous chromosomes will pair up during meiosis 1. And it doesn't really matter if the alleles are different, right? Like if you go, this gene from your dad had a different allele than this gene from your mom, because the two alleles are going to be similar enough that they're still going to interact together. The X and the Y chromosome do still line up side by side during meiosis 1 because there's a portion on the Y chromosome that matches a portion on the X chromosome. There are actually two portions on the Y chromosome that match two portions on the X chromosome. And if this fails, if you don't separate these properly during anaphase 1 or anaphase 2, we get what's called nondisjunction. And again, if nondisjunction happens during meiosis 1, all 4 cells are impacted. If nondisjunction happens during meiosis 2, only the cells that descended from the abnormal cell are impacted. And this says nondisjunction is most common in the sex chromosomes. That's not saying it happens more frequently in the sex chromosome. That's saying that embryos that develop from gametes that had nondisjunction happen, they're more likely to survive if nondisjunction happened in the sex chromosomes. That our cells are better able to tolerate differences in the number of sex chromosomes because guess what? Males already have less X chromosomes than females do. Right? So we're already programmed with an ability to control the different numbers of X chromosomes. Because every female mammal has 2 and every male mammal only has 1. So our bodies can work with only 1 X chromosome. Meaning you can have females that only have 1 X chromosome and no Y and no separate X. Okay? Or you can have males that have 2 X chromosomes instead of just 1. Because we have the mechanisms in place to deal with that. Anyways, we'll talk about that. Maybe we'll talk about that a little bit more later. I don't think we will talk about it more, but not today. We'll talk about it when we talk about Mendelian inheritance and non-Mendelian inheritance patterns. I don't know you. Sorry, somebody's trying to talk to me. Yeah.
So the chromosomal mutations, is that like Down syndrome? Would that be
Yes. Yeah, and so Down syndrome is the one when non-disjunction happens in what we call our autosomal chromosomes, our non-sex chromosomes, that has a pretty decent survival rate, is Down syndrome. There are a couple of others. There's Klinefelter and Turner are both in the sex chromosomes. There's Edwards syndrome that has a very low survival rate, but you do sometimes get survival, and I think that's a trisomy in the 18th chromosome. And then there's also on chromosome 13. It has a very low survival rate, but you do get some individuals that will survive with a third copy of chromosome 13. All right. What are our sources of variation? And what is the advantage of having these mechanisms to increase variation? Why is it nice that you're not a genetic copy of either of your parents, that you're a combination of the two, right? What's the advantage of that? All right. So we have two ways to increase variation in meiosis. The first one, which we talked about, recombination. Okay. So the first one, recombination. And basically this provides an unlimited combination of chromosomes. Now it's not actually unlimited. There's obviously going to be a limit, but we have enough combinations there that it's virtually limitless. We have way more combinations possible than gametes you'll make during your entire lifetime. Okay? So recombination can facilitate making more varieties of gametes than the number of gametes that you can make during your lifetime. And the other one is independent assortment. Now, independent assortment, and these are gamete mechanisms. And let me show you independent assortment for a moment. I'm going to call our chromosomes, I'm going to call them P and M. Just so you know, it's the paternal chromosome and it's the maternal, okay? So we've got chromosome 1, and we'll call this 1P and 1M, okay? So it's chromosome 1, and you've got the paternal and the maternal version of that chromosome, okay? And then we've got chromosome 2, the P and the maternal. And we've got chromosome 3, the P and the maternal, okay? And we're like, cool, well during metaphase 1, they all line up at the equator of the cell, and they're always going to line up this way, right? That all the paternal are on the left and all the maternal are on the right. That's how it's always going to happen, right? I love how you all are nodding your heads. You're like, yep. No, there's no reason why this would happen. It's completely random. Because you could have this, or you could have this, right? There's no reason all the paternal need to line up on the left and all the maternal on the right. Or you could have this. Oh man, this is... Right, you could just as easily have that. We call this independent assortment. That there's nothing saying that all the paternal chromosomes need to end up on the left and all the maternal. You should be able to anticipate that this wouldn't happen anyways because they actually mix during this process, right? During prophase 1, you've got crossing over. And so it's like, well, if there were some signal that would just say that all the paternal need to be on the left, you might have moved that signal over to the maternal chromosome, right? Does that make sense? A little bit? Okay, so our number of combinations is equal to our number of chromosomes. Because at this position here, how many options do we have? We've got 2. The paternal could be on the left or the maternal could be on the left, right? We have 2 options at this chromosome on how, or at this location on how our chromosomes can be positioned. Okay, we have 2 options. How many options do we have here? 2. How many options do we have here? 2. So our total number of combinations, because of the independent assortment, Our total number of combinations is 2 raised to the power of the number of chromosome pairs. 2 raised to the number of chromosome pairs. How many chromosome pairs do we have in our cells? 23. Which means the total number of combinations is 2 to the 23rd power, based on independent assortment. What is 2 to the 23rd power? That's a huge number. Let me see. 8,388,608. Which means even if crossing over never happened, you can make over 8 million different gametes. Now, if you are a male mammal, you're going to make 8 million gametes in a month. But if you're a female mammal, you're not going to make 8 million gametes in your entire life. So it's still a significant amount. But then when we start saying crossing over can happen, we can basically make almost an unlimited number of chromosome combinations. Now again, it's not unlimited, but it's so big of a number that you're not going to make anywhere close to that number of gametes in your lifetime. So for all intents and purposes, it's basically impossible. It's basically impossible. Okay? Does that make sense? So those are the ways we increase variation at the level of gamete formation. But then on top of that, we've got random fertilization. So in theory, every single sperm has an equal opportunity to fertilize the ovum. Right? Now typically only one ovum is going to be released at a time, unless, or at least in humans. In other mammals, you might release multiples, which is how you can have litters of, more than just one. But in theory, every sperm has an equal opportunity to fertilize that ovum. And every sperm is genetically distinct from every other sperm. Right? And so these are the ways in which we increase variation. And the benefit of this is it ensures that there's a pretty good chance that at least some of your offspring are going to survive. Right? Because the reality is your offspring are going to live in an environment that isn't exactly like the one you live in. Now, this isn't really true for humans because we pretty much make our environment whatever we want it to be, right? It's like, you want to live somewhere that's cold, you put a heater in your house and in your car and you wear coats, right? It's like we create our environment, we make our environment what we want it to be. Like, why would you want to live someplace cold? I don't know, I don't. Although it actually... it gets down to 50 degrees sometimes in the morning. It's pretty chilly, Oh, it's just so, oh gosh, it's so fun. I lived in Ohio for 4 years, and, people there, it's like you get, when winter starts to show signs of ending, it's like a high of 35. And you're like, oh man, it's been a high of 15 for so many months. This feels wonderful. And people are in like flip-flops and shorts, and it's 35 degrees outside. And then you move back to Southern California, and it's like you get into October, and all of a sudden it drops to like 60 at night, and people are like in a parka and Ugg boots. I was like, I can't take it. It's so cold. It's just funny. And so what this allows you to do is, it allows you to kind of scramble information and make it to where as the environment changes, because if you're a human, natural selection plays a very small role in human evolution because we pretty much make our environment what we want it to be, right? But other things play a larger role. But if you're just some random animal, I don't know, pick any random animal. You're a duck-billed platypus, okay? You may be really successful at your current environment, and that success is being carried out that you're living long enough to have multiple litters over multiple years. But the reality is the environment your offspring face are going to be a little bit different than yours. So you might be really successful, but if you made genetically identical offspring, they might not be successful in a changing environment. But if you make offspring that are a little bit different than you, some of them are going to be less successful, but some of them will be even more successful than you are. Okay? It's just like, listen, I was an okay football player. I love football. But I didn't get a chance to play it after high school because I was just an okay football player. My son is 5 years old and is more athletic now than I ever was in my entire life. I mean, it's just, I mean, it's amazing. And I know people say this about their kids all the time. Like, other people tell me this about my kids. And I hear, and then of course you're like, oh yeah, people are just going to tell you things that are going to flatter you. I overhear people that don't even know he's my kid talking about this. Like, he's a freak. My son is like one of those kids that it's just like, they were just born to be an athlete. And it's certainly not, I mean, it didn't come from me. I mean, it came partly from me and partly from my wife's family. And he just got a really sweet combination to where he has incredible hand-eye coordination. He's super coordinated, and it's just fun. Like, it's just fun to watch. And it's like, I don't know what he's gonna do. Maybe he'll end up hating sports, and he'll just, even though he'll be athletic, he just won't ever play. That's okay, I guess. So what this does is it forces us to remember that natural selection can only work if you have variation in place. If every individual is genetically identical to every other individual, natural selection can't favor anyone, right? You have to have variation. And so the sexual reproduction and gamete formation provide variation necessary for natural selection be able to change allele frequencies and make a population better fit for its environment. And that's why when you sample a random population at a random place, they're pretty well fit for the environment that they live in. And then how does using meiosis make individuals more fit? The reality is it might not increase your fitness, but your fitness isn't just determined by your ability to produce offspring. Your fitness is determined by your ability to produce offspring that survive and reproduce themselves. Because it doesn't matter if you produce more offspring than every other individual, but all of your offspring don't survive long enough to reproduce, or all of your offspring are sterile. Like, if you cross a horse with a donkey, they're going to form offspring, but those offspring are sterile. And so essentially, those offspring have a fitness of 0, even though those mules, I mean, they're just going to rock life. You put however much weight you want on them, and they're going to take it wherever you want it to go. Wonderful animals. But their fitness is 0. Yeah.
I don't know if this is too much of a divergent question, but what causes sterility?
Yeah, it varies. It varies from case to case. I think with the horse and the donkey is that their chromosomal number is slightly different, and so that the gametes will fuse, and they only have the proper number of all of those chromosomes. So physiologically they're normal, although they're really powerful like horses, and then they have great endurance like donkeys. But then when they go to do meiosis and to make gametes, they're one copy of a chromosome that they got from the donkey, and it doesn't have a counterpart from the horse. When they go to line up side by side during meiosis 1, it fails the checkpoint because there's no second chromosome, and so meiosis won't happen. Yeah.
Could there be some mutation where you can get past that, somehow another chromosome or something happens?
To where you could actually get them to be able to reproduce? Yeah, so I mean, I don't know why we do this, but we think it's fun to make animal hybrids. It's like we'll make ligers and tigons, it's just like it can never happen. 1, they live in completely different places, and then 2, if you put a male lion with a female tigress, the tigress is probably going to kill him. Okay, because male lions, they're really lazy, they don't really do anything. I mean, he might put up, I don't even know what would happen. But so they'll artificially inseminate a female tiger with sperm from a male lion, and then you'll get a liger. But most often they're sterile. And again, it's because you've got an issue of chromosomal number, and so they just can't make gametes properly. But every now and again, you can get that checkpoint to fail. That checkpoint doesn't stop the process, so it still continues, and you make gametes. And then every now and again, you can get those gametes to actually fuse, and you can get an individual that isn't sterile, but it's very unusual. Very unusual. So I don't know why we like to do this, but we do. I guess it's kind of cool to have a liger or a tigon. Yeah.
If they manage to get a liger or 2 ligers, male, female, where both the checkpoints failed, so they were not sterile, would they be able to continue the line? Probably so. Yeah. And then would their offspring be sterile, or would it not?
I don't know. That's an excellent question. Now, when checkpoints fail, you've got a lot of issues. right? Because checkpoints are there for a reason. Checkpoints are protecting against, are you looking at a Tygon?
Yeah.
Yeah. Or is that a Liger?
It says Ligers and Tigons.
Yeah. Tygons are huge.
Yeah.
Like-
It's
Yeah. I mean, they're enormous. They've like whatever there is, like checking the growth of a tiger, like it erases it when you get a Tygon, and you get things that are just massive. They're impressive animals. Okay. All right. Right now we're going to take a little bit of a lecture break, and I know it's a little bit late, but we're going to do it anyways. And what I want you to do is this. So think back to when we were talking about crossing over, and I want you to put on paper 2 chromosomes, like 2 versions of chromosome 1, and I want you to show me that why it increases the number of variations to a number that's so high that you're never going to make enough gametes to come to that. Because crossing over, it seems really simple, right? You've just got one place where they cross over, and so I want you to draw those on paper and show me how we can really increase the number of combinations. Take about a minute. Feel free to work with those around you and see what you can do, but put something onto paper.
That's a great question. Answer her question. It's all your where are you getting one quick 5. So like 47%.
Yeah, but 47%. But then you had general Asian markers, right?
Yeah.
Okay, so the next several slides in our PowerPoint are basically going to demonstrate this, and also demonstrate what I already drew on the board with that we can basically, we have 2 options at every chromosomal position. The paternal chromosome can be on the left, or the maternal can be on the left. And so when we actually reconvene and start, we're going to move to that last important question. But before we do that, I want you to really be able to see what this looks like when you start putting crossing over down on paper. You draw 2 chromosomes, and you start to demonstrate how our number of combinations are almost limitless. Okay? And so I'm going to draw our 2 chromosomes with the same color. Okay, so here we've got 2 versions of chromosome 1. These are 2 copies of chromosome 1. They are associating together during meiosis 1, and during prophase 1, crossing over happens. Okay? The way we tend to draw this is like, hey, there's like one place on the chromosome where crossing over happens, and it'd be like right here. Right? Where we just like, okay, we take this part and we exchange them on the chromosomes. But the reality is there are literally thousands, if not tens of thousands of places where this can happen on this chromosome. It might happen here. It might happen here. Okay? Or it might happen here. Or it might happen here. Or it might happen at all 4 of those places. Or it might happen at 3 out of 4 of those places. 2 out of 4 of those places. And then maybe it'll be here and here. And then maybe it'll be here and here. Maybe it'll be here and here. And you see this with literally thousands, if not tens of thousands of places on the chromosome where you can cross over. You can literally form so many different types of chromosomes that you will never make 2 gametes that are genetically identical. And then when you add on top of that that the gametes that you're making late in your life are different than the gametes you're making early in your life because your germ cells have accumulated mutations during your life. And it's like there's no way you're ever going to make two gametes that are exactly the same. Is that cool? Like the gametes you're making when you're like you just reach sexual maturity are different than the gametes you're going to be making in your 40s. Because in that 30 years, you've accumulated mutations in that germline that weren't present when you just reached sexual maturity. Okay? And so basically, just the number of combinations we can make is just astronomically large. Okay? And you're like, that's so cool. And then on top of that, the gametes that you're making, every gamete you make has chromosomes in it that have never existed before. And it's kind of a nice reminder of how complicated all of this is. We tend to make it look very simple, and it makes sense why we do that so we can learn it efficiently. But it is really complicated. It is really complicated. All right? Any questions? So does this make sense? And you should have something like this on paper, I don't know, just in case a week from now you're asked a question on how do we increase variation during gamete formation. Oh, it wouldn't be a week from now because this material's not, you're right, this material's not going to be on exam 2. Touche. 5 weeks from now when you're taking your final exam, and if you're asked to do something like this, like to ask where does the increase in variation come from, might be nice to draw 2 versions of chromosome 1 and to show that because we can have crossing over happen in multiple locations, we've got a whole bunch of different types of chromosome 1 that we can make. Okay. No questions? All right, so the last questions from these slides. When does meiosis occur? When does meiosis occur? And so meiosis in different organisms, different animals, happens at different times. Or at least in different eukaryotes. In almost all animals, it happens in the process of making gametes. Happens as you're making gametes. Prior to gametogenesis finishing. It is your mechanism of gametogenesis. So this is what happens in almost all of our animals. That in order to even make gametes, you have to go through meiosis. Now, in plants and some fungi and algae, it happens after fertilization. So you'll get your diploid plant stage that will undergo meiosis to make the haploid stage of the plant. You get this alternation of generations. And then in between here, you basically have fertilization happen and then a whole bunch of steps of mitosis before you finally go through meiosis. But the actual gametes, they're not formed by diploid cells. The gametes are formed by haploid cells through mitosis. In some fungi and algae, meiosis happens immediately after fertilization. That is, 2 diploid cells will fuse together to form a tetraploid cell, a cell that has 4 copies of the genome, and then that cell will go through meiosis to restore the diploid state. And if you want to ask the question of what is the advantage of doing meiosis at any of these given times, there isn't an advantage or a disadvantage of doing. It's just different. It's just different. It's always wonderful. You're like, if it's different, how did it become different if all of these descended from the same eukaryotic ancestor? Was that your question, Levi?
No.
Oh, okay.
I was going to ask, so if you do meiosis immediately after fertilization,
Yep.
do you get kind of a mosaic effect in the organism?
Yes. Yep. Yeah. That you would have absolutely. You would have 2 different. You would have basically cells that were different genetically. Yeah. But some organisms are not as sensitive to that as others. Animals are pretty sensitive to that because most animals have some kind of an immune system that's able to detect foreign material. And so if you have two different, genetic lineages, then your body needs to detect both of them as self. But in reality, it would usually detect one of them as self and everything else would be foreign. Yeah. Okay. So here's plants. The gametes are formed by a haploid stage. So you see this haploid stage, it says N, which means what? One copy of the genome. So this entire stage of the plant only has one copy of the genome. The gametes are made by undergoing mitosis. Those gametes fuse to form our diploid life stage of the plant. And then a long time after that diploid stage of the plant will finally undergo meiosis to form cells that will develop into these gametophytes. And then here's some fungi and algae. So we've got a fertilization taking place. In this case, the fertilization is by two haploid cells forming a 2N cell that will immediately go through meiosis because the actual multicellular organism is always haploid. Okay? But in some of these, the multicellular organism is diploid, and so your zygote will actually be tetraploid, and then we'll go through meiosis to form a diploid stage. Okay? So in animals, it follows the pattern of basically what we've been talking about this entire week, that as you make gametes, you go through meiosis. That's the goal of meiosis, to make haploid cells that can develop into gametes. Okay? Any questions? All right. So please, even if you've already sent me your study guide and you want to send me a second copy, feel free. And if you haven't sent one yet, it's not a bad idea to send me your study guide. You might enjoy what I add to your study guide, especially come Friday.